Good afternoon, Professor Schmidt. You should be able to unmute yourself now.
Yes, I try
I can
to
hear
do
you.
it. Now,
I can hear you.
should, yes.
Good. Alex, the session, do you want me to introduce Professor Schmidt or?
Yeah, no, you can go ahead.
Dear all, it's my pleasure to welcome my research collaborator and esteemed friend, Professor Heidi Schmidt, to start this session, this sessional school on circuits and systems, AI chips in future here. If you have had dug Professor Schmidt's work, her work on BA4 memristors is stellar. And she has, in parallel, she heads 3 different groups in 3 different institutions, one on quantum systems, other on thermal systems, and finally also on memristive systems. It has been a pleasure to work with her. She did her diploma physics, which would be equivalent to the Indian masters and or BSc and MSc in the rest of the world, from Leipzig, and then did her PhD there as well. And then she got a massive Attract Award from Fraunhofer Society, which is 2.5 million euros. She currently heads a group in Leibniz Institute of Photonics Technology, holds a chair in University of Jena while leading the group in Fraunhofer ENAS. We would be delighted to hear more about memristors and her work, and we are very thankful to her. So over to you, Professor Schmidt, and I look forward to listening to your comments.
Welcome, everybody. I hope you can hear me.
We can hear you.
Yes, okay, perfect. I would like to thank the organizers of this seasonal school from IEEE to invite me to give the first tutorial in this long list of exciting tutorials here. And my focus will be today on a special type of hardware elements, passive hardware elements, which are well suited to develop energy efficient AI hardware. And in the main property of the 2 types of hardware elements I will present here is that they are electroforming free. The affiliation I'm using here is from University of Jena, but as Bhaskar already said, I have also affiliations in other 2 parts from Germany. Let's start here with this simple sketch. What you see here is a sketch taken from the famous work from Professor Leon Schur, who theoretically predicted the existence of a novel passive device, which was missing so far. He predicted in 1971.
Professor Schmidt, if I can pause you, I don't think you're sharing your. Are you?
Okay, that's.
It's perfectly fine to hear, but if you are sharing something.
So now it should work.
Yes.
Can you see the screen? Sorry.
Yes, we can see the screen. Thank you.
Because I was pointing to this sketch here. Here you see the 4 passive devices, and this one here in the bottom in the right corner is this BFO memristor, or a memristor in general, a passive device, which has been theoretically predicted by Professor Leon Schur in 1971. So now, 50 years later, we are at the point that I can present today to you worldwide first ideal analog memristor, but this is then during the talk I will give today. The talk will be structured as follows, and this tutorial for sure I will start with thanks because we are working since 2008 on this topic, and they are mainly 2 scientists, Dr. Nandu and also Dr. Danilo Burger, who are working in my team from the very beginning, and there are many other PhD students and also master students who worked together with me. We raised a lot of funding to fund all our work, and the outline of my tutorial will be as follows. I will motivate why do we need such passive devices which are electroforming free. And I will motivate it using a well-known memristive device, which is the titanium dioxide memristor, which has the property that it needs an electroforming step. And then I will switch to the new types of electroforming free memristors. The one is the bismuth iron oxide memristor, which is a bipolar and analog. And here we have then in the third part of this tutorial, we will have the electroforming free unipolar memristor, yttrium manganese oxide and holmium manganese oxide. And for both types of those passive devices, I will start, because it's a tutorial, to explain the characteristic properties, and then I will give applications which can be derived from those properties. Let's start with the motivation for developing novel passive devices. So passive devices only have two electrodes, two contacts. Let's call them T1 and T2. And here you see a single switch, and here you see a switch aligned in a 3D array. And it's typically it's formed from solid materials. It's switchable between two or more states, and one can use either voltage or current to change the resistance of this passive device. There are main advantages. One of the most important one is the unification of memory and information processing at the same place, which goes alongside with the energy efficient working principle of such passive devices called memristors, which is a word coined from memory and resistor. And then the reconfigurability of the resistance states is non-volatile. They are very simple in their structure. They are CMOS compatible, for example, can be integrated back end of line. There are many materials which could be elaborated to form and to show this functionality of memristors. And what is well known from the very beginning, they can emulate brain functionality. What you see here is this part of the motivation. State of the art are memristors, for example, hafnium oxide or titanium oxide, which need an electroforming step. What does it mean? Let's start with the typical work of a material scientist developing memristors. Such material scientists have to form memristive material, which is, let's say, embedded between two electrodes, T1 and T2, and this memristive material is this black box here. And normally, let's say the state-of-the-art memristors work as follows. If you apply the first time a bias to this between the two electrodes, for example, this is the black line if it's a negative bias, or this is also here the black line if it's a positive bias, you ramp it, and then the corresponding current only increases above a certain compliance level if this forming bias is very large. And if you ramp it, then the bias, the second and third and farther on, then you do not need such a large bias to change the resistance state of this memristor between high resistance state with a small current and low resistance state with a high current. And this step that you need, this property that you need an electroforming step with a large bias to bring this memristor into functionality is called electroforming. And it has several disadvantages if you go towards an array of memristors where you have to address then step by step all the memristors which are formed in this array and which have to work later on with the same small writing bias which we see after the electroforming step. The well-known explanation for such an electroforming step is the formation of filaments. I could imagine that maybe you already heard about it, how electroforming is explained. So let's take the special case of an hafnium oxide memristor. This is the hafnium oxide here between the top electrode and the bottom electrode. And what you see is a schematic sketch which explains the formation of filaments, and which explains why you need in the beginning at least once a large bias. So you need this large bias to form this filament between the top and the bottom electrode. And then this is the electroforming step. And if this is done, you have formed this filament, and then the system is switched from the high resistance state where there's no filament bridging top and bottom electrode to the low resistance state. This is the first step we see here. This is the first bridging step. And then it goes further. Then you can interrupt this filament by applying a very small bias. This is called reset, right? So, but the filament is only broken in a small range, not the whole filament is broken, but it's just broken here. And then you make a set process, and here you do not have to bridge such a long distance, it's just a very small distance, and therefore the set bias after the electroforming step and after formation of the first filament is very small. And this then here you can cycle within those 4 pictures, and you see electroforming is related with the formation of filaments. And actually, if one needs a material which does not need this electroforming step, then you have to look for. And just to summarize why it's really important to look for such materials, I would like to summarize the properties of membristors where electroforming is needed. I mean, one can also control the resistor switching after the electroforming, if this electroforming is possible. However, the number of applications for such membristors which need electroforming step is rather limited. And this is related with the step that they cannot easily be without any selection transistors be integrated in 2D or 3D arrays of memristors. And there's another impact. If you need such selector transistors for memristors which have an electroforming step, then this electroforming has a strong impact on the design of crossbar arrays, right? Because for every memristor here, you need a selector and selection transistor. And then you have to make a trade-off between the area of the cross points and the area of the forming circuit. And for sure, also the forming transistors need additional area. So there are several disadvantages if you think about upscaling and increasing the number of memristors if those memristors have and need an electroforming step. And this was the motivation for our work. We wanted to see and to look whether there exist other materials where the resistor switching has a different physical mechanism underlying resistor switching and where no electroforming step is needed. And this brings us to the first example of the first part of electroforming free memristors. This is the bismuth iron oxide memristor. The structure is exactly the same. You have a passive device with a top electrode and with a bottom electrode, and it's a polycrystalline device. And now comes the difference. The difference is that here, the resistor switching is not related with the formation of filaments, but it is related with the reconfiguration of the barrier height of the top electrode and of the bottom electrode. I will explain this in the following a little bit more in detail. Just to give you a tiny idea, a small idea about the structure of those materials, though the bismuth iron oxide memristors we are developing, they have a typical thickness between 300 and 600 nanometer, and they are deposited on a bottom electrode, which is typically platinum, by a pulsed laser deposition. Where does this reconfigurable barrier height comes from? We just, out of luck, one of my first students working on this research topic used some titanium in the bottom electrode material during the growth. This was out of luck. And this titanium plays a very important role. It's a trap. This titanium is a trap and incorporated in the bismuth iron oxide host lattice. And what for is this titanium a trap? It's a trap for the oxygen vacancies which are present in this oxide material. It's n-type conducting, right? And those oxygen vacancies are mobile if the electric field between top and bottom electrode is large enough. If the electric field is very small, and this is, for example, electric field related with the reading bias, the readout bias, then they will not drift, because the drift velocity exponentially increases of such ions, exponentially increases with the electric field. And if the electric field is small, nothing will happen. The oxygen vacancies will not be redistributed. However, if we apply a negative bias to the top electrode, the positively charged oxygen vacancies will drift towards the top electrode. And if there are traps available, traps which are the titanium ions incorporated in the bismuth iron oxide lattice, they will capture the oxygen vacancies at the position of the top electrode. That means oxygen vacancies are at the same time donors. And we have a concentration, a very large concentration of donors close to the top electrode. That means the barrier height of the top electrode is reduced because we have there a large concentration of donors. Okay, that means the top electrode is ohmic, non-rectifying, and the bottom electrode, because there are nearly no oxygen vacancies left, is rectifying. So we have a Schottky diode, which is reverse biased. On the other hand, if we apply a positive bias to the top electrode, then oxygen vacancies drift towards the bottom electrode, yeah? Because they're attracted by this bottom electrode, by this field here, by this negative charge. And again, if we incorporate titanium traps in the bismuth iron oxide host lattice, then those traps can catch and capture the oxygen vacancies close to the bottom electrode. And again, if we remove then the writing bias and the electric field, which causes the drift of the oxygen vacancies, they are kept then at the position of the bottom electrode. And in this case, the bottom electrode sees a very large concentration of donors. The barrier height of the bottom electrode is tremendously reduced. It's non-rectifying. And the top electrode is getting rectifying because there are nearly no oxygen vacancies left. That means with the redistribution of oxygen vacancies under application of the writing bias and independence on the polarity of the writing bias, we can determine which barrier height is reduced, is large, and which barrier height is very strong. And then we can make this in a fine-tuned manner, and I will show you how many applications can be derived from this very nice property. It's not a filamentary switching, it's a switching which depends on the area of the top electrode and of the bottom electrode. And this is a very nice scalable, and it needs no electroforming step. So let's let you show what is measured first. For sure, the first step, we ramp the voltage as usual, right? And then we record the current. This is plotted here as the absolute value of current. So for example, if we start in the high resistance state, we bring the voltage to the positive part, yeah? Then the system, this bismuth iron oxide resistor, is switched then from high resistance to low resistance state. Then we ramp the voltage back in the state, and then we ramp the voltage towards the negative value. For example, here we attract the oxygen vacancies to the top electrode. Top electrode becomes non-rectifying, as you can see here, and then it switches from the high resistance state back to the low resistance state. Okay, and now it depends, as I already said, on the polarity of the writing bias, which state the system will be in. For example, if we apply a positive writing bias, what is the case here, then the top electrode is rectifying, the bottom electrode is non-rectifying, and we see this characteristic curve. And if we apply a negative bias to the top electrode, the bottom electrode is rectifying and the top electrode is non-rectifying, and we see this characteristic curve. That means the polarity of the writing bias determines which curve we see. On the other hand, also the polarity of the readout determines whether we can read out a large or a small readout current, right? And this is then also very important. So we have in total 4 states we can reconfigure into the system. And this is very unique because with 4 states you can make all the 16 Boolean functions and emulate them with a simple passive device. And it's not just a Boolean function because the amplitude of the writing bias determines whether it's complete maximum value of the low resistance state or whether we have intermediate values. So, and because the system can take on intermediate values of the barrier height and with that of the readout current, we have here the possibility not only to realize and emulate the Boolean logics, but the analog logic, which is called fuzzy logic. So all the states here along this line can be read out if we apply a positive readout bias, and all the states can be read out if we apply a negative readout bias. So, and then are the main properties of the bismuth iron oxide memristor. And if we read out a system with a small readout bias, which does not shift and drift the oxygen vacancies, then we can either read out a system which is in this state, yeah, in the, let's say, Schottky forwarded bias Schottky diet, or if you apply a negative writing bias, if we have applied a negative writing bias, we can read out the states of this negative reverse bias Schottky diet. Yeah. So now we try to understand and to analyze the dynamics of the system, because it's clear, for sure there's a transport of ions of the oxygen vacancies, right, between top and bottom electrode. How long does it take? How does it depend on the amplitude of the writing bias? And this was the question we asked ourselves. And we also wanted to prove, our idea on this barrier height, which is changing with independence on the polarity of applied bias. So the barrier height we could easily determine using impedance measurements. And this is something after having put the system into the low resistance state or into the high resistance state, we determined then the barrier height of the top electrode and of the bottom electrode using impedance measurements. And here you see barrier height is 0.35 electron volt for the top electrode, and top electrode plus bottom electrode is 0.43 electron volt. And then one can also make let's say, a simulation using console in that case. What is the extension of the depletion layer between the top electrode in low resistance state, and in high resistance state, we have a depletion layer below the top electrode and above the bottom electrode. And one can calculate how large is the extension of the depletion layer in dependence on the barrier height of those two, of the top and of the bottom electrode. Now comes the interesting point, which is really new and which we really investigated for those bismuth iron oxide memristors. There's a very old theory from 1940, even much older than the theoretically predicted existence of the forced passive device of the memristor, right? And this theory tells us how the drift velocity of ions depends on the electric field in the system, and also depends on a typical barrier height, which has to be overcome by the ions in the potential, crystal field potential of the Horst lattice. So what you see here on the sketch is a, let's say, very much zoomed in sketch. You see here the position of the top electrode, of the bottom electrode, and you see the oxygen vacancies. So they are of interest now in the experiment I'm showing here, because we wanted to determine, is it indeed possible to increase the velocity of writing, the writing speed in the system tremendously just by changing the electric field we apply, right? So, and what we did is we had two parameters we could vary. If we apply a rectangular writing bias pulse, then we can vary the length of this writing bias pulse, for example, between 100 milliseconds and 500 nanoseconds, and the height of this, and the amplitude of this writing bias. So here we vary it between 6 volt and 22 volt, as you can see. And then we know if we apply a positive writing bias, then the oxygen vacancies will drift towards from the top electrode to the bottom electrode. This is shown here. This is the direction of the drift of the oxygen vacancies under application of the positive writing bias. And this barrier has to be overcome. And in addition to that, the amplitude of this writing bias determines the electric field, which is here labeled with E prime. And there's another possibility. I mean, if we apply a negative writing bias to the top electrode, then the oxygen vacancies have to drift from the bottom to the top electrode. And also there's a barrier height for this process. And also there's dynamics into it. Okay. And then we modeled everything. And we have seen that indeed the drift velocity of oxygen vacancies scales exponentially with the electric field. And this is very interesting because from free carriers, for example, from holes and electrons in silicon, we know that there is a saturation drift velocity for such free carriers for electrons and holes. And that's not the case for ions, which are actually hopping over the potentials of the crystal field. And then the drift velocity of such ions depends exponentially on the electric field which is applied. Yeah, but what does it mean for the application of such transistors? What you can see here is the writing voltage. This is the amplitude of the rectangular bias we applied, positive direction. And we always put the system before we made a new experiment into the higher resistance state. And then we successively increased the writing voltage amplitude and had a look when has the system switched from the high to the low resistance state. It means when was there enough time for the oxygen vacancies to drift from the top to the bottom electrode to overcome the 300 up to 650 nanometer thickness of this bismuth iron oxide memristor. Okay, we started with the 100 millisecond long pulse with an amplitude of 6 volt. We know this is the standard, let's say, writing procedure we apply, and then we know it can be switched from high to low resistance state. And this current level we took as let's say, as a reference. And then if we reduced the width of this writing bias from 100 millisecond to 50 millisecond, we had to apply a writing voltage amplitude of 6, 7, 8 volt. Only then the system could, I mean, if we apply a shorter bias, right, only with a larger amplitude, we could then provide and drift enough oxygen vacancies from the top to the bottom electrode. Okay, if you reduce the time, the writing voltage time much more to 1 millisecond, we had to apply a voltage of 9 volt and so on and so on. 50 microsecond, 1 microsecond, 500 nanosecond, we had to apply a voltage of 17 volt, and 50 nanosecond, we had to apply a voltage of 24 volt. Okay, but this is very interesting, one can say, and one sees it already, because between a writing time of 100 milliseconds and 50 nanoseconds, there are more than 6 orders of magnitude difference. And the corresponding amplitude of the writing voltage just changed by a factor of 4. 4 orders, and here a factor of 4. This is extremely important because the system, due to this exponentially dependent drift velocity of oxygen vacancies, shows a huge dynamic range in the resistor switching. Okay, now I described all the properties of bismuth iron oxide membristors you have to know to understand in the following some applications and to see and to come with the motivation for more applications. What you see here is famous image motivating the development of ideal analog passive devices. In AI we are using, we used until 2018 digital devices, passive devices with a high precision. And the number of operations which could be performed with such devices per watt was somehow limited, and it was not possible to bring and to continue with the development of AI circuits with such digital passive devices of high precision. Therefore, starting 2019, one used digital devices with reduced precision. And this will go on as projected maximum until 2023, because also then there are not enough operations per watt which can be performed by such digital passive devices in AI circuits, even if they have already a reduced precision. Therefore, because of this energy-hungry devices in AI circuits, it's predicted that it's absolutely necessary to have analog devices, passive devices, which have to be used in such AI circuits starting from 2023. And now you can ask, yeah, what are the properties of such analog devices? And I will try to give you a very, let's say, simple explanation how one can decide whether the device which has been developed, for example, the memristor which has been developed, is such an analog device which might be useful for the AI circuits starting 2023. This is the definition. What you see is the blue points, some blue points, yes, they are superimposed by the orange points here in the, let's say, positive polarity of writing pulses of different amplitude. And then here you see after the polarity of the writing bias has been inverted, you all again see blue points, which are on a nice line, and then you only see one orange point on which is somehow abruptly changing and not following such a line. What is plotted here is the readout current of a memristor. Let's call it a readout current of an analog passive device. And the ideal memristor should show a continuously changing readout current of the memristor with continuously changing amplitude of the writing bias. And after the polarity of the writing bias has been inverted, it should be possible to bring the readout current successively back to the initial value. So far, there exist memristors which fulfill the condition in this, let's say, polarity range of the writing bias. But as far as I know, only the bismuth iron oxide memristor, as I will show you in the following, is so far the only existing memristor which shows also after the polarity of the writing bias has been inverted, the decrease of this readout current independence on the amplitude of the writing bias. I will prove this in the following because we made now for this tutorial a plot which reminds you the plot I've shown here. Let's call it, this is the definition plot of an ideal analog memristor. What you see here is the resistance at the reading voltage of +2 volt of the bismuth iron oxide memristor. And this is the amplitude of the write bias in units of volt. So if we just use a small bias, right, of -2, then nearly nothing is changed. If we have then a larger bias applied, we can increasingly change the resistance state of this memristor. You see here it's up to 2 orders of magnitude change in resistance, that's fine. And then we can invert the polarity of the voltage pulse and then again start with a very small amplitude of the write bias. And then we can bring the system successively back to the initial state. And that are experimentally determined values. And if you compare it with the existing non-ideal functionalities of published data of memristors, then you see here that this curve nicely corresponds to the definition of an ideal analog memristor. And it's really motivating to see then those memristors later starting 2023 in the AI circuits. But to go this way, it's still much work to be done. And I will show you and present to you some applications we are envisioning. But before I do that, I will also give, because it's a tutorial, some explanation how is this further characterized memristor. Because the first thing is, how long can this new resistance state be reconfigured into this memristor? And in order to analyze that, one defines, for example, the low resistance state or the high resistance state, and then one reads out, this is more readout bias, the resistance state of this memristor continuously. So this is shown here. This is called retention, retention of such memristor. This is the resistance in the high resistance state, which is read out over a time up to 35,000 seconds. And the low resistance state retention looks like that. And the ratio between resistance and high resistance state and in low resistance state is larger than 10. This is a condition which has to be fulfilled. Another type of retention can also be done for the memristor I've shown before, where 2 barrier heights are reconfigurable. So you have 4 states, and also for the 4 states, one can read out the resistance state after having written the state into the system. And then comes another type of characteristics, which is even more challenging when such a memristor material is developed. This is called endurance. Endurance means how often can you cycle between low resistance state and high resistance state. So what you're doing is writing low resistance state, read out, writing high resistance state, read out. This is the first cycle. Then the second one, low resistance state, read out, high resistance state, read out, and so on. And the goal is to have as large as possible number of cycles before the memristor breaks. Let's put it in that simple way. And this is shown here also for bismuth iron oxide memristor, resistance, and then up to 200,000 cycles. And you see we have written and changed this between high resistance and low resistance state cycling. And we have read out then this resistance state. And again, resistance between high and low resistance state is this ratio is larger than 10. So now comes another type of motivation, which has been added by an, let's say well-known motivation. Everybody knows the amount of data is tremendously increasing. That means it's exponentially increasing. So that's the reason why we need novel hardware for the AI circuits in the future. And this is also demonstrated by this, now it's already rather old. In the beginning, AI has been applied for the gaming, for the chess, for Jeopardy, and also for AlphaGo. And here you see the power consumption, how this already increased with increasing number of operations which is needed by the AI computer, which played again the experts, the human experts. But this is just gaming. Yeah, I'm calling it just gaming. It's also important, but what is more important for us in the future is, for example, autonomous driving technology. There, it's predicted that there's such an expected higher energy consumption due to increased mileage, due to increased data transfer and infrastructure, that with the existing hardware elements in AI, we will never manage to realize an energy efficient autonomous driving technology. So, and here we have to go ahead, we have to develop and to bring novel devices, energy efficient devices into these circuits, which are, for example, used then later on in autonomous driving technology. I will give an example which was, let's say, well known for all groups developing memristors. The first check was, can the memristors emulate synaptic functionality? So, and what I'm showing here in the sketch is just a very technical, as you can recognize, but this should be the sketch of a biological synapses to be clear. So what you see here is the presynaptic neuron, the postsynaptic neuron, and this is the synaptic cleft. And as we all know, there is a presynaptic neuron signal superimposed by the postsynaptic neuron signal, and then it depends on the time delay between both signals whether the width of the synaptic cleft will be changed or not. And this behavior, the dependence on the width of synaptic cleft on the time delay between the signal from the pre and the postsynaptic neuron is called spike timing dependent plasticity. And all groups tested their memristors with respect to the spike timing dependent plasticity, whether the memristor can emulate spike timing dependent plasticity. So what is, that's the reason why it's sketched that way. So we take the top electrode as the presynaptic neuron, we take the bottom electrode as the postsynaptic neuron, and we take the bismuth iron oxide material as the synaptic cleft, just to show this. But now we don't have the width of the synaptic cleft change, we change the resistance state of the synaptic cleft. And the idea with this time delay between those two signals is also taken from biology. So here you see the typical shape of such a spike from the presynaptic neuron and from the postsynaptic neuron, first a rectangular spike and then an exponentially decreasing, and here also a rectangular spike and then exponentially increasing. And this is the time delay. This is very important. This is the time delay between the two spikes, and only if this time delay is small enough, the resistance state of the, in that case, of the bismuth iron oxide memristor will change. Yeah, and then you can have a positive time delay, or you can have a negative time delay because post-spike is before the pre-spike, or here the pre-spike is before the post-spike. So what we did is we checked this. This is the typical synaptic functionality also of the biological synapses. Therefore, it's plotted that way, the time delay here between the two signals. And then this is the state of the resistance state, in that case, of the bismuth iron oxide memristor. And you see, if the time delay is very small, there's a huge change of the resistance state. If the time delay is large, there's nearly no change. And now comes this high dynamics into play. 10 milliseconds is the typical learning window of biological synapses. Therefore, we started with a learning window of 10 milliseconds. But then, just by increasing slightly the writing amplitude, we could reduce the learning window to 1 millisecond, to 500 microsecond, and also to 50 microsecond. And this is rather interesting because, in contrast to biological synapses, which have to learn in this 10 millisecond time window, you with the artificial synapses, for example, based on bismuth iron oxide, you can tremendously reduce this learning, the learning window, the time window for the learning. And then also the energy consumption is kind of interesting. So the human brain, this synapses needs, one synapses needs 10 E-3 picojoule per operation. Let's put it that way. And here, for example, the bismuth iron oxide artificial synapses need 4.7 picojoule per change per applied switching and neural signal. Okay, so this is still a factor of 100 up to 1,000 larger than in the human brain, but we don't have to emulate this difficult structure of this human brain completely. We can reduce the structure tremendously, and then also realize some learning and some neural networks based on such artificial synapses. What I will show in the following is just a short summary why I'm saying we can make information processing and information storage. Information storage is clear now because resistance stage is changed in a non-volatile manner. Information processing is explained here once again. There are also other memristors which show this type of double hysteresis. We call it double hysteresis, current versus voltage, right? And but they have the disadvantage that one can only use the polarity of the writing bias to define a certain logic. Yeah, they have here a rather abrupt switching, and this does not allow to use the readout, the polarity of the readout bias to define which state is read out. And here, in contrast to that, we have the polarity of the writing bias and also the polarity of the readout, which determines which state is addressed here. And we can clearly address then 4 states. And with that, as I already said, one can realize logic gates for the Boolean functions, and also logic gates if it's in an analog manner for the fuzzy functions. So we can realize learning in neural networks with such bismuth iron oxide memristors, where the bismuth iron oxide memristors are used as a weight, as an analog weight, for example. So, and this is shown here. It's not only the information processing. I mean, if you think about this spike timing dependent plasticity I've shown before, it's just the 10 millisecond time window for learning. Then you see here we have only long term potentiation and long-term depression curve if only one parameter is if only the bottom electrode is reconfigurable. And if we have both reconfigurable, the top and the bottom electrode, then we have those curves which are well known, and we have additional curves. So one can realize also with the bismuth iron oxide memristor with a double hysteresis, bidirectional learning, and then on a very fast time scale. So, and in addition to that, this is the work we did together with Professor Schubey. We just showed this year that the memristors are also robust against noisy input data. So this is the ideal input, but you will never see from neurons such an ideal input. It's always noisy, right? And what we did is we checked, can this bismuth iron oxide memristor still emulate spike timing dependent plasticity if the input is noisy? So we checked the spike timing dependent plasticity for different noisy input data, and we showed that indeed, I jumped directly to that. If the input has no noise, that are the blue curves, as you can see here, and up to a noise of 30%, it's still the spike timing dependent plasticity one can see here and emulate with such bismuth iron oxide memristors. This is very interesting because this brings us to an application which is called edge computing. So maybe you are aware of the last year message from Elon Musk, who showed that he developed a Neuralink chip, and so far the data cannot be processed within the chip because this would be too the energy consumption for this data processing would be too large. So they had to be transmitted the data first, and then they had to be processed outside. The idea for the edge computing is to introduce some data processing close to the data source. And we think that such energy efficient passive devices, for example, as the bismuth iron oxide memristor, could be used to have some data processing. The data are noisy, analog data, which are recorded in such neuroimplants. And then one could, before transmitting them, already reduce the amount of data and already have a pre-analysis of such data. That's a very interesting application, we think, which might be promising. And another application, which I will not focus on here in this talk because I'm running out of time, is to use such memristors as physical unclonable function. This is for secure electronics. And the main idea about that is that we have here a very small error rate in such bismuth iron oxide memristors, and in the same time we have a large variability if we compare different bismuth iron oxide memristors, and this large variability during fabrication, and then together with this small error rate in this, if you ramp the same memristor, brings us to the application of such bismuth iron oxide memristors as physical unclonable function. I will jump over it because I would really like to introduce you to a novel type of memristor, which is also electroforming free, which is unipolar, and which has, again, a completely different, let's say, physical mechanism underlying this electroforming, this resistive switching. So what is not new is the structure. You have, again, a top electrode, a bottom electrode, but the material has been exchanged. Now we do not have bismuth iron oxide anymore. We have yttrium manganese oxide or holmium manganese oxide, as I will show in the future. What is the underlying mechanism? Here, the density of vortex states that are charged states of those ferroelectric materials, they have charged domain walls, they have charged vortices, and those vortex states, the density can be changed when you ramp the writing bias between top and bottom electrode. That's very interesting because also for that you do not need an electroforming step. So we have here a unipolar memristor with a very large on-off ratio, which can be up to 10 to 6 even, and this is huge in comparison to the 10 to 10, 10 to 1, 10 to 2 for the bismuth iron oxide memristor, but it's unipolar. So the polarity of the applied writing bias does not matter. No? It's just you can, using the electric field, which you ramp, let's say from 0 to 18 volt in that case. Okay, I take this value here, or from 0 to even to 30 volt. Here the system is in the high resistance state. Also here it's in the high resistance state. And then in that case, in the high resistance state, the density of the vortices of those charged filaments of electrons or holes is very small. And then here at this point, the density is abruptly changed. and then you have a large density and the system jumps into the low resistance state. And this is also electroforming free, illustrated here. So here you have a large density of vortices of charged filaments, and here you have a small density of vortex states, and this is related with the high resistance state, and this is related with the low resistance state. The interesting point about this type of memristor is that you can nicely tune, very nicely tune the set voltage and also the controllability or the randomness of the set voltage and of the reset voltage. And this brings me just to an outline of the possible applications of this type of memristors, in addition to use them as a selector, because the on-off ratio is so large. So what we write, and just to show it, we write the material and then we realized different set voltage ranges and different reset voltage ranges for those memristors. And also here one can check the retention, as you remember. One sets the system into the low resistance state, large current, or into the high resistance state, small current, and then one reads out the state, as the readout current, as for a long time. And for example, here we read it out for 1 day. It's very stable. And then the other thing, which is also done and which shows that it's there's something special about this memristor. We have here we change the contact size. And in the high resistance state, the contact and the resistance scales with the contact size. This is expected for an area dependence for a capacitive system. And in the low resistance state, it really does not depend on the contact size, because here we have a dominating vortex charged filament, which is not dependent on this on the contact size of the top contact in that sense. What you also see from the sketch is that the polarity of the writing bias, here negative, here positive, does not play a role. And that we can vary here the on-off ratio. It ranges here in that case 4 orders of magnitude. This is very huge, right? So, and we checked because there are many manganites which can be selected and which show this behavior of vortices and of charged domains. We did not only, because we started with yttrium manganese oxide, and next step we took holmium manganese oxide. It's also ferroelectric, has such vortex states, and we showed that also for this material one can have the same, and one can nicely tune it. This is a top view on the sample, and just topography. It's polycrystalline, again, very simple. And we used here 2 different thicknesses, as you can see. In the one case, the holmium manganese oxide, which is this electroforming free unipolar memristor, has a thickness of 425 nanometer. And in the other case, it has a thickness of 580 nanometer. And then we analyzed the retention, as you can see here, the stability of the resistance after 1 day, during 1 day. And we also checked the dependence on the contact area. And this is what we already know. The contact area of the low resistance state, so this is the normalized contact area. So here the high resistance state does not, so this depends on the contact area, and the low resistance state does not depend on the contact area. So then we made a model. We wanted to analyze and to understand how does the switching depend on the formation of depletion layers in the system. In this, we took the 2 samples, holmium manganese oxide, where we know they have 2 different thicknesses, and we have also seen that the switching behavior is really different. So first we made some impedance measurements to understand what is the extension of the depletion layer below the top electrode, above the bottom electrode, and in this undepleted region. How thick is the undepleted region of the system? We modeled this, the impedance data, as you can see here. The symbols are the measurement data, and the scattered lines are the model data. And from that, we developed an understanding about the switching, resistive switching in the system, and how it depends on the polarity and also on the the vis of this layer. So what you can see here and what fascinated us was that the set voltage in the negative bias range is predictable. So you see there's not a randomness in the set voltage, but in the positive bias range, the set voltage is random. The same applies for this system here, for this sample. The set voltage is predictable in the negative bias range, it's random in the positive bias range. So by understanding the resistance switching mechanism underlying the system, we can then tune and realize a system where we have predictable and random set voltage. That's not bad. And then we made a model and we showed with an equivalent circuit diagram and also with the corresponding energy diagram how the set voltage is determined by the formation of vortex states within the depletion layer, within depleted and undepleted layers, right? And we have shown that if we have this positive bias applied, which is shown here, then we have to expect a random set voltage. And if we have a negative bias applied, which is shown here, we have to expect a predictable set voltage because the whole layer is undepleted and there's a predictable voltage drop over the whole system. Okay, and there's also an outlook, how can we apply such manganites, yttrium manganese, manganite oxide, and also the holmium manganese oxide and the other manganites for sure, because if the set voltage and the reset voltage is random, then one can use the system as a random number generator. That's very interesting for cryptography, for crypto elements, but you can also use it as a switch, as it's shown here, and which is a very large on-off ratio and with a very good retention. So you can use it as a selection element, for example, in crossbar array structures. I will jump over the characterization of the use of yttrium manganese oxide as a random number generator, but here you can see how this is typically done. This is a different structure where you have randomness in positive and negative bias range, and then you just have a look at the distribution of set and reset voltages, and then you can extract some ideas about the entropy of the system. Okay, so now I would like to summarize my talk. In this tutorial, I presented the idea of this theoretically predicted passive element memristor, which unifies data processing and data storage. And I motivated the development of electroforming free memristors because only electroforming free memristors can be used in crossbar array structures without any selection transistor. So, and one electroforming free memristor is this bismuth iron oxide memristor, which is not only electroforming free, but also bipolar. It's analog and bipolar. And I have also shown you that so far the only existing passive element, which is fulfilling the conditions for an ideal analog device. And we have seen that in 2023, it's expected that such analog devices will be used in AI circuits, for example, for energy efficient autonomous driving. So they are robust against analog noisy input data, and this can be used in edge computing. And because of their variability in the fabrication, they can also be used in secure electronics, for example, as physical unclonable functions. And then I presented two types of memristors, which are also electroforming free, but unipolar, where the resistance state change does not depend on the polarity of applied writing bias. I presented yttrium manganese oxide and holmium manganese oxide. They are ferroelectric and with charged domain walls. And one can control the resistor switching, whether it's random or predictable, by the depletion layers within the manganite system, depletion layer extension between above the top electrode and below the bottom electrode. And if we think about the random resistor switching, then there's the possibility to apply this in secure electronics, for example, as a random number generator. I would like to thank you for your attention. And again, the organizers for giving me the opportunity to give the first tutorial here in this very nice school, seasonal school. If you're interested in our work, just contact me. It's just by email. I will answer immediately. And here you see finally the summary. I hope at least that you can take this message with you. There are the 4 passive devices, and the one we are needing for this, for the novel AI circuits is the ideal analog memristor. Okay.
Many thanks, Professor Smith. This was very, very thought-provoking and quite a lot of information. All I can say to people who are listening, particularly in the last slide, when Professor Smith said that if you're interested, write to her and she'll respond quickly. I can vouch for that. She responds to my emails even before I think my brain has stopped the thought of sending it to her. So she's very quick on that. But before I open to any other question, I'm sure we'll be running out of time very soon because I see Alon who has joined here. One of the things which we as circuit designers who always had this trouble was the reset voltage or set voltages of memristors are around +5 voltages, 5 to 10 volt. And if you have millions or billions of memristors, then there is a problem which we would consider that there will be a lot of energy being dissipated. Is there anything physically stopping these voltages from being reduced? Or do you see in future we might see memristors with 1 volt or 2 volt or in that range set or reset value with small dynamic ranges available?
Yes, I mean, it depends. I mean, when you wish to develop this analog memristor, you will for sure need this larger set voltage, 5 volt, minimum 4 volt, I would say. Otherwise, it will not work, right? For the unipolar memristors, there is a huge, I mean, one can reduce for sure the set and reset voltage by changing the material. That's possible because it's different functionality. But for the analog memristors, I don't see this chance. No? But one should keep in mind that the energy consumption, I mean, also depends on how long you apply this bias. No? And as I have shown, we have this, let's say, high dynamic range of writing and changing the resistance state in bismuth iron oxide memristors. So the writing time can be tremendously reduced, and with that also the energy consumption which is needed to change the resistance state. So this is the way out we see here to reduce the energy consumption.
Thank you. Alex, I'm cautious of the time, so should we move on to the next one and give people time to send questions by email rather than taking questions now?
Yeah, I guess you could they could type their questions onto the chat, and we can
pass it on to Professor Schmidt.
Okay, that's a good idea.
Have a very good Sunday and enjoy the rest of your day.
Yes, thanks a lot. Have a nice summer school. Bye-bye.
Bye-bye. Thank you.
Alex,
Bye-bye.
over to you to introduce.
Yeah, so we would, because, hi, Alon.
Good evening, everybody.
Yeah,
good evening, Jamie.
Yeah, so Professor Chua, he is not able to join today because of his health reason. So he gave a message to read out. So probably we can do that right now, and soon after that we can move to your talk.